In 1959, the Coventry factory floor of Armstrong Siddeley was building the backbone of Britain's nuclear deterrent. But despite engineering one of the most successful turbojets of the early Cold War, the company's name was about to be permanently erased. The numbers did not suggest a failing business. Just 7 years earlier, in 1952, their Sapphire engine had shattered expectations, passing a brutal 150-hour type test at a staggering 8,300 pounds of thrust. It was so relentlessly capable that the American military bought the production license to build it as the Wright J-65, bringing a massive influx of foreign capital into the Midlands. For the Coventry machinists who built it, and the Royal Air Force crews who depended on it, the Sapphire was mechanical certainty. It powered the Handley Page Victor B-1 bombers waiting on cold dispersal pans, and drove the heavy Gloster Javelin interceptors through the freezing British sky. The company had successfully mastered the brutal transition from old piston radials to slim, high-compression gas turbines. And yet that engineering triumph could not save the brand. The paradox of the Armstrong Siddeley Sapphire is that it did not lose its identity because it lacked power or reliability. It lost its independence because the political and financial architecture of British aerospace was buckling under the escalating costs of the jet age, forcing a ruthless wave of state-mandated corporate consolidation. In 1959, Armstrong Siddeley was swallowed to form Bristol Siddeley, and a famous Coventry mark vanished into corporate architecture. But the real story of the Sapphire is not only the story of a surrendered name, it is the story of how a British Aero engine bridged the critical gap between the piston past and the supersonic future, only to be devoured by the very industry it helped to build. Every week we tell the stories of British engines, factories, and industrial names that once taught the country what power sounded like, and what happened when the market moved on. Subscribe if that history matters to you. The story begins not with nostalgia, but with a specific place in a Coventry drawing office in 1948. The story of the Armstrong Siddeley Sapphire begins with a national mechanical deficit. By 1947, the British aviation industry had won the Second World War on the strength of the piston engine and had entered the jet age on the strength of the centrifugal compressor. Engines like the Rolls-Royce Nini and the de Havilland Goblin were centrifugal flow jet engines, power plants that drew air in and flung it outward using a large spinning impeller before forcing it into combustion chambers. They were relatively simple to build, highly reliable, and immensely powerful for their time. But they had a fatal aerodynamic flaw. They were wide. The large frontal area of a centrifugal engine created a massive wall of drag. As the Cold War dawned and the requirement for aircraft shifted from subsonic fighters to supersonic interceptors and high-altitude nuclear bombers, the Royal Air Force realized that they could no longer push a fat engine through thin air. Britain urgently needed a successful axial flow engine, a turbine engine where air passes straight through a series of spinning compressor blades, allowing for a much slimmer profile, lower drag, and higher compression ratios. The blueprints for Britain's next leap forward did not actually begin in Coventry, but in Manchester, at the heavy engineering firm Metropolitan Vickers. Commonly known as Metrovic, the company had been quietly pioneering axial flow gas turbines since the early 1940s. They had successfully built the F-2, which evolved into the Barrel, an engine that briefly powered the experimental Saunders-Roe SRA-1 flying boat fighter. By 1947, Metrovic was developing an even larger, vastly more powerful axial design, designated the F-9. But building experimental prototypes is entirely different from supplying a national air force. Metrovic was fundamentally an industrial electrical engineering company, facing the staggering financial and manufacturing commitments required to mass-produce a military Aero engine. An engine built for aircraft use, where power, weight, reliability, and certification mattered differently from road vehicles. The company made a strategic decision. In 1947, Metrovic exited the aviation business entirely to concentrate on industrial steam and gas turbines. The British government, operating through the Ministry of Supply, could not afford to let the F-9 design die. Rolls-Royce was already struggling with the early development of their own axial flow engine, the Avon. The government needed an insurance policy, a second engine program to guarantee that Britain's upcoming V-bombers and interceptors would have the power they required. In 1948, the Ministry of Supply transferred the entire F9 project, the blueprints, the prototypes, the tooling, and the leading engineering staff, to Armstrong Siddeley in Coventry. For Armstrong Siddeley, this was an astonishing industrial gamble. The Coventry mark was deeply respected, but their reputation had been built on a completely different kind of mechanical philosophy. They were famous for the Cheetah, a highly reliable radial engine, a piston aircraft engine with cylinders arranged in a circle around the crankshaft. Throughout the Second World War, the Cheetah had powered thousands of Avro Anson training aircraft. It was a machine of pistons, push rods, cast aluminum cooling fins, and predictable steady heat. Now, the engineers at the Parkside and Ansty factories in Coventry were being asked to master the Axial-Flow Turbojet. This was not merely an upgrade, it was a shift in the fundamental physics of manufacturing. A piston engine could tolerate minor variations in casting and machining. An axial-flow gas turbine could not. The F9, which Armstrong Siddeley immediately renamed the Sapphire, required a compressor section containing hundreds of tiny, aerodynamically perfect aerofoil blades. These blades had to be forged, machined, and hand-finished to tolerances measured in the 10,000ths of an inch. Inside a British machine shop, the Sapphire demanded an entirely new kind of workforce. The foundry workers and machinists of Coventry had to learn how to work with new, heat-resistant alloys that destroyed traditional cutting tools. If just one of those hundreds of compressor blades contained a microscopic fracture or was slightly out of balance, the harmonic vibration at 8,000 revolutions per minute would tear the engine apart on the test stand. Despite the terrifying manufacturing learning curve, Armstrong Siddeley threw the full weight of its industrial capacity behind the project. By late 1948, the first Coventry-built Sapphire prototypes were bolted to heavy test stands in the Midlands. The noise was something Coventry had never heard before. Not the rhythmic, thumping roar of a piston radial, but a high-pitched, deafening shriek that tore through the damp English air, smelling heavily of aviation kerosene. The early reception in the trade press and within the Ministry of Supply was cautious but deeply optimistic. The initial runs proved that the fundamental Metrovic design was sound, but it was Armstrong Siddeley's rigorous testing and metallurgical improvements that began to turn the theoretical F9 into a weapon of war. By 1950, a pair of early Sapphires were strapped into the outboard nacelles of a modified Avro Lancastrian testbed aircraft, taking the engine into the sky for the first time. For the mechanics and test pilots evaluating the new power plant, the Sapphire was a revelation. It delivered immense thrust for its frontal area, and crucially, it showed signs of being remarkably resistant to surging. The dangerous phenomenon where an axial compressor stalls, starving the engine of air and causing a sudden, violent loss of power or catastrophic fire. By the early 1950s, the British aviation establishment realized that the Sapphire was no longer just a backup plan for the Rolls-Royce Avon. It was rapidly becoming a genuine rival. The blueprints were ready, the test beds had survived the heat, and the Coventry machinists had mastered the blades. But to turn a prototype into the backbone of the Royal Air Force, Armstrong Siddeley had to prove the engine could survive not just on a test stand, but in the cold, thin air of the jet age. In 1952, inside a heavily reinforced test cell in Coventry, the Armstrong Siddeley Sapphire was subjected to the British aviation industry's most brutal mechanical examination, the 150-hour type test. It was not enough for a jet engine to produce high thrust for a few minutes. It had to survive prolonged periods of maximum thermal stress, simulated combat power, and rapid throttle changes without suffering structural failure. When the engineers finally shut down the fuel flow and unbolted the inspection panels, they found a machine that had not merely survived the test, but had dominated it. The early production Sapphire cleared the 150-hour mark, producing a continuous, verified 18,300 pounds of thrust. To put that figure into industrial perspective, just a few years earlier, standard British jet engines were celebrating half that output. The Sapphire had instantly become one of the most powerful turbojets on the planet. The secret to this immense capability lay in two critical mechanical choices that Armstrong Siddeley had successfully refined from the original Metrovic blueprints. The first was the axial flow compressor. an engine design where air is forced straight back through alternating rows of spinning and stationary blades, rather than being flung outward by a single large impeller. In a British design office, an axial flow engine meant that an aircraft could finally be aerodynamically slim. It allowed the heavy Gloster Javelin, Britain's new all-weather interceptor, to tuck two Sapphires tightly against its fuselage, keeping the aerodynamic profile narrow enough to slice through the dense, freezing air over the North Sea while hunting radar contacts. But building an axial flow compressor was a manufacturing nightmare. The Sapphire required hundreds of individual compressor blades, each forged from advanced alloys, machined and hand-polished. On the factory floor in Coventry, this meant an entirely new standard of precision. If a machinist left a microscopic flaw in a single blade, the harmonic vibration at maximum revolutions would shatter the compressor, sending razor-sharp shrapnel tearing through the engine casing. Armstrong Siddeley had to train a workforce accustomed to the forgiving tolerances of cast iron and aluminum pistons to work with aerospace alloys that dulled standard cutting tools in minutes. The second major breakthrough was the annular combustion chamber, a continuous, uninterrupted ring where fuel and high-pressure air are mixed and ignited rather than relying on separate individual combustion cans. In the foundries and machine shops of the Midlands, building an annular chamber meant mastering severe, continuous heat distribution. If the fuel nozzles were slightly misaligned or the airflow was uneven, the combustion ring would develop a hot spot and burn a hole straight through the outer casing. Armstrong Siddeley's metallurgists and engineers solved the puzzle, creating a chamber that delivered a smooth, intensely hot, and highly stable flow of gas to the rear turbine blades. What truly separated the Sapphire from its main domestic rival, the Rolls-Royce Avon, was its throttle response and stability. Early axial flow engines were notoriously temperamental. If a pilot advanced the throttle too quickly, the compressor could stall, spitting a ball of fire out of the intake and immediately killing thrust, a highly dangerous event known as surging. The Sapphire, however, proved to be remarkably surge-resistant. For a Royal Air Force pilot scrambling from a damp runway in Lincolnshire, this meant the throttle could be slammed forward without hesitation. The engine simply spooled up, shrieked, and delivered power. This combination of brute force and mechanical stability did not go unnoticed across the Atlantic. In a rare reversal of post-war industrial dominance, the United States military realized they did not have a domestic engine that could match the thrust and reliability of the British turbojet. In a landmark industrial agreement, the Wright Aeronautical Corporation purchased the manufacturing license to build the Sapphire in America. Redesignated as the Wright J65, the British-designed engine was heavily adopted by the United States Air Force and Navy. It would go on to power a massive fleet of American combat aircraft, including the Republic F-84F Thunderstreak and the Martin B-57 Canberra. Over 10,000 J-65 engines were eventually built in the United States. For Armstrong Siddeley, the American licensing deal was a colossal financial breakthrough. It brought a massive influx of foreign capital into Coventry, allowing the firm to expand their research facilities, invest in new tooling, and cement their position as a top-tier aerospace contractor. They were no longer just a company building reliable piston engines for training aircraft. They were a global player in the high-stakes economy of Cold War aviation. Back in Britain, the engine's power meant that airframes often had to be adapted to handle it. When Hawker Aircraft sought an alternative power plant for their legendary Hunter fighter, they found that the Sapphire pushed the aircraft so hard that the Hunter F2 and 5 variants had to be carefully engineered to digest the sheer volume of air the engine demanded. Meanwhile, Handley Page selected the Sapphire to power the Victor B-1, the most advanced of Britain's V-bombers. The V-bomber force was the ultimate expression of British strategic power, and the Victor relied on 4 Sapphires buried deep in its crescent wings to carry a nuclear payload to high subsonic speeds at over 50,000 feet. The Coventry firm had successfully built a machine that commanded respect from the British government, the Royal Air Force, and the American military. The Sapphire had proven it could run reliably on the test beds of Coventry, but its true test was about to begin on the dispersal pans of the Cold War. By the mid-1950s, Armstrong Siddeley was no longer just adapting a borrowed design. They had transformed their Coventry production lines into one of the most vital aerospace foundries in the Western world. The Parkside and Anstey factories were running day and night, vibrating with the continuous machining of high-temperature aerospace alloys, the casting of complex turbine housings, and the relentless shriek of test beds proving each engine before it left the Midlands. The company that had built its reputation on the steady, rhythmic thumping of the piston-driven Cheetah had now fully conquered the axial-flow gas turbine. At its peak, the Sapphire was not just a successful engine. It was the mechanical heart of Britain's Cold War defense strategy. In a Britain where an engine could decide whether an aircraft lifted from a damp airfield, a lorry made its delivery, a motorcycle carried a rider through the night, a bus left the depot, a racing car survived the next lap, or a nuclear bomber held the line of deterrence in the freezing stratosphere, power was not an abstraction. It was metal, fuel, labor, heat, sound, repair, risk, and trust. For the Royal Air Force, that trust was placed squarely on the Sapphire to power two of the most critical aircraft in the nation's inventory. The first was the Gloster Javelin. As the threat of high-altitude Soviet bombers grew, the RAF demanded an all-weather day and night interceptor. The Javelin was a massive, heavy, delta-winged machine, packed with early, cumbersome radar equipment. To get that much weight off the ground and up to 50,000 feet in minutes required immense, immediate thrust. Armstrong Siddeley provided it by supplying twin Sapphires, tucked closely against the Javelin's broad fuselage. On the dispersal pans of RAF Odium and RAF Luchars, the sound of a Javelin scrambling became a defining noise of the era. The ground crews would connect the starter carts, and the Sapphires would spool up with a high-pitched, tearing scream that vibrated through the chests of the mechanics standing on the tarmac. When the pilot pushed the throttles forward, the axial flow compressors swallowed massive volumes of damp British air, the annular combustion chambers ignited it with absolute stability, and the heavy fighter was hurled into the sky. But the engine was not static. It was evolving. The early SA-6 variants had proven themselves at 8,300 pounds of thrust, but the Coventry engineers knew the architecture could handle more. Through relentless metallurgical refinement and compressor redesigns, they developed the SA-7 variant, which shattered the 10,000-pound thrust barrier, eventually delivering over 11,000 pounds of thrust without the need for an afterburner. It was an astonishing mechanical achievement for a firm that, just a decade earlier, had been primarily known for radial engines making less than 500 horsepower. This relentless power meant the Sapphire was chosen for the ultimate expression of British aviation ambition, the V-bomber force. While the Vickers Valiant and Avro Vulcan relied on Rolls-Royce and Bristol engines, the Handley Page Victor B1, arguably the most aerodynamically advanced of the three, was built around four Armstrong Siddeley Sapphires. Buried deep within the roots of the Victor's distinctive crescent wing, the four Sapphires gave the massive strategic bomber the ability to cruise at high subsonic speeds at altitudes where the air was incredibly thin and the temperature dropped to minus 56 degrees Celsius. At bases like RAF Gaydon and RAF Cottesmore, the Victor fleet sat on quick reaction alert. If the klaxon sounded, the ground crews had only minutes to bring four highly complex gas turbines to life simultaneously. The Sapphire's legendary resistance to compressor surging meant that Victor pilots could demand maximum power instantly, pushing four heavy throttles to the stops without fear of the engines choking or flaming out. The Coventry firm had achieved what seemed impossible. They were building engines that rivaled, and in some metrics exceeded, the best that Rolls-Royce could offer. The factory floor was secure, the export royalties from the American Wright J65 were flowing in, and the Royal Air Force was heavily dependent on their engineering. But scale brings its own intense vulnerabilities, and building a world-beating engine was about to prove infinitely easier than surviving the economics of the aerospace industry. By 1956, the Sapphire had grown from a successful engine into an entire industrial ecosystem. To keep the Royal Air Force flying, Armstrong Siddeley had to maintain a relentless supply chain of spares, technical manuals, and specialized aerospace alloys. The Coventry foundries were pouring metal at an unprecedented rate, producing the thousands of high-precision compressor blades required for routine fleet maintenance. An overhaul, a major service process where an engine is taken apart, inspected, and rebuilt to operating standards, for a high-performance turbojet meant completely stripping the machine to check for microscopic heat fractures. On RAF bases from Lincolnshire to Scotland, dedicated teams of mechanics learned the exact mechanical habits of the Sapphire. trusting its surge-resistant design implicitly and knowing exactly how to tune the fuel flow for maximum efficiency. At the Anstey test facility just outside Coventry, the noise of maximum thrust testing became a permanent fixture of the local environment. When a Sapphire SA-7 was run up to its maximum limit on the test stand, the sheer volume of air being compressed and ignited created a low-frequency vibration that rattled windows miles away. The rear turbine stages operated in a continuous, blindingly bright inferno, with exhaust gases exiting at near supersonic speeds. To survive this, Armstrong Siddeley had to master the machining of mnemonic alloys, advanced heat-resistant metals that were notoriously difficult to cut, shape, and polish. Yet despite the immense thermal and mechanical violence happening inside the casing, the engine remained famously smooth. The factory workers who assembled them knew they were building more than just power units. They were building the physical shield of the British Isles. This was the absolute peak of Armstrong Siddeley as an independent aerospace power. They were not merely a subcontractor, nor were they living in the shadow of Rolls-Royce. Through the mid-1950s, the company held its own at the very pinnacle of global aviation. The American royalties from the Wright J-65 production, which ultimately saw over 10,000 engines built in the United States, poured millions of dollars of foreign capital into the British economy. This wealth allowed the Coventry firm to expand their research and development, plotting out even more powerful turbojets, turbofans, and experimental rocket motors. For the pilots who strapped into the Gloster Javelin with No. 46 Squadron in the dead of night, the Sapphire was a deeply personal piece of machinery. In the freezing rain of a Cold War scramble, when an unidentified radar contact was detected over the North Sea, there was no time for delicate engine management. The pilot needed to slam the throttles forward and feel the immediate, heavy shove of over 16,000 pounds of combined thrust. The Sapphire delivered that violence reliably, every single time. It taught a generation of British aviators to trust the Axial-Flow Turbojet, not just as a fragile engineering experiment, but as a robust, dependable tool of war. By the time the Handley Page Victor B-1 bomber entered active squadron service with No. 10 Squadron in 1958, Armstrong Siddeley had cemented its legacy. They had taken an abandoned Metropolitan Vickers prototype, solved the manufacturing nightmare of the axial compressor, and turned it into a world-beating strategic system. The Coventry workforce had fully mastered the jet age, transitioning flawlessly from the radial piston engines of the past to the high-compression turbines of the future. The engine bays were full, the airfields were loud, and the company's order books appeared impenetrable. The Sapphire was performing perfectly in the sky, but on the ground the political and economic weather of British aviation was turning cold. The first crack in Armstrong Siddeley's empire did not happen in a compressor stage or a combustion chamber. It happened on a balance sheet. By 1956, the Sapphire was a proven, world-class triumph, but the fundamental economics of the British aerospace industry were beginning to warp. This was the brutal reality of the cost of iron, aluminium, fuel, and manufacturing. Developing the early Sapphire had been incredibly expensive, but pushing the company's jet engine program into the supersonic era required a level of financial endurance that was beginning to stretch the independent Coventry firm to its breaking point. To move from the high subsonic speeds of the Handley Page Victor bomber to the sustained Mach 2 requirements of the next generation of interceptors, engine manufacturers had to completely rewrite their metallurgical rulebooks. The friction and heat generated by supersonic airflow meant that standard aerospace alloys were no longer sufficient. Companies had to invest heavily in exotic titanium forging, massive supersonic wind tunnels, and vastly more complex, heavily reinforced test beds. For Armstrong Siddeley, a fiercely independent firm that still built luxury motor cars alongside gas turbines, the research and development costs were astronomical. They were pouring millions of pounds into future designs, operating on the assumption that the British government would reliably buy them. In April 1957, that assumption was destroyed. The Minister of Defense, Duncan Sandys, published the infamous 1957 Defense White Paper. It was a political document that would fundamentally break the trajectory of British aviation. The government concluded that the era of the manned fighter and the strategic bomber was effectively over, and that the future of British defense lay in unmanned guided missiles. In the drawing offices at Coventry, where engineers had spent months drafting the supersonic successors to the Sapphire, the impact was immediate and catastrophic. Entire aircraft programs were canceled overnight. The thin, swept-wing interceptors that would have carried the next generation of Armstrong Siddeley turbojets were wiped out by a political signature. For the mechanics and machinists at the Parkside and Ansty factories, the sudden shift in government policy was a profound shock. The factory lines were still busy, turning out Sapphire SA-7 engines for the Gloster Javelin. But an engine plant cannot survive on current production alone. It requires a continuous, guaranteed pipeline of future work to justify the immense cost of maintaining foundries, high-precision machining lines, and a highly skilled workforce. When the future orders evaporated, the financial strain on Coventry became an existential threat. Simultaneously, a technological rival was emerging that directly threatened the Sapphire's hold on the V-bomber fleet. The Sapphire was a pure turbojet, an engine that derived all its thrust purely from a high-speed exhaust jet. But across the Midlands in Derby, Rolls-Royce was perfecting the Conway, Britain's first bypass engine, now commonly known as a turbofan. A turbofan moves a portion of its intake air around the core combustion process rather than forcing it all through the fire, making the engine significantly more fuel efficient for long-range cruising. When Handley Page began designing the upgraded Victor B-2 bomber, the Royal Air Force demanded greater range, heavier payloads, and higher thrust. Despite its legendary reliability, the pure turbojet architecture of the Sapphire could not match the fuel economy of the new bypass technology. The ministry selected the Rolls-Royce Conway to power the Victor B-2. Armstrong Siddeley was abruptly cut out of the ultimate future of the V-bomber force. The government was acutely aware that the British aviation industry was now too fragmented to survive the shrinking defense budget and the rising costs of technology. There were simply too many proud, independent companies chasing a rapidly diminishing pool of contracts. The Ministry of Supply issued a ruthless ultimatum to the entire sector: consolidate or starve. State funding for future projects would only be awarded to large, newly formed corporate conglomerates. The Sapphire had proven that Coventry could master the jet age, but the new political reality dictated that engineering brilliance was no longer enough to guarantee survival. The company was about to face a forced marriage that would erase its name forever. In 1959, the political pressure finally overwhelmed the Coventry firm. Armstrong Siddeley was forced into a merger with its former competitor, Bristol Aero Engines, creating a new state-approved aerospace giant, Bristol Siddeley Engines. In an instant, the proud Armstrong Siddeley mark, a name that had built the famous Cheetah Radial, mastered the Axial-Flow Turbojet, and powered Britain's nuclear deterrent, was erased from the front lines of British aviation. The physical foundries and machine shops at Parkside and Ansty did not shut down overnight. They continued to overhaul existing Sapphires, build spare parts, and supply the Royal Air Force squadrons still flying the Gloster Javelin and the Handley Page Victor B-1. The American royalties from the Wright 65 continued to flow across the Atlantic, but the independent engineering soul of the company was gone. The Coventry workforce was no longer designing the future. They were merely servicing the past. The ultimate corporate takeover for the old Armstrong Siddeley engineers came just 7 years later. In 1966, the British aerospace industry underwent its final, massive contraction. Rolls-Royce, the Derby firm that Coventry had fought so fiercely to rival, purchased Bristol Siddeley entirely. The monopoly was complete. The Coventry facilities, once the fierce heart of independent jet engine development, were absorbed into the vast Rolls-Royce empire, reduced to a subsidiary role in a much larger corporate machine. Out on the airfields, the Sapphire fleets were slowly losing their battle against time and technology. The Gloster Javelin, despite its immense thrust, was increasingly obsolete in an era of supersonic missile carriers. As the 1960s progressed, the heavy interceptors were steadily withdrawn from frontline service, their twin Sapphires howling for the last time over RAF bases before the airframes were towed away to the breakers' yards. The Handley Page. Victor B-1 bombers survived slightly longer. Many converted into aerial refueling tankers. They continued to drag heavy fuel loads into the sky. The four Sapphires buried in their crescent wings, proving just as reliable in the tanker role as they had in the nuclear strike role. But eventually, airframe fatigue and the relentless march of turbofan efficiency caught up with them. The era of the pure, fuel-thirsty turbojet was over. The mechanical triumph of the engine could not outrun the changing economics of the industry. The design was brilliant, but it required an independent industrial ecosystem that the British government was no longer willing to support. The engine still ran. The development money stopped. The government forced the merger. The Coventry name was erased. Rolls-Royce bought the remnants. The production lines went quiet. The aircraft aged out. The sound faded. The independent industry it powered was gone. The company had vanished into corporate architecture, but the physical engines they left behind had not yet finished their work. Today, the Armstrong Siddeley name does not exist on any modern corporate registry. Unlike Jaguar, which survived through endless ownership changes, or Triumph, which was successfully resurrected for a new era, the Coventry aerospace mark was entirely extinguished. When Bristol Siddeley was ultimately swallowed by Rolls-Royce in 1966, the old Armstrong Siddeley identity was not kept as a heritage badge or a prestige subsidiary. It was simply deleted from the British industrial record. The famous Parkside factory, the historic beating heart of the company, where the first Sapphire prototypes shrieked into life on the heavy test stands, was eventually closed and demolished, its physical footprint replaced by university buildings and urban redevelopment. The massive Anstey site survived much longer as a Rolls-Royce facility, focusing on marine and industrial gas turbines, but the specific culture of the men and women who built the Cheetah and the Sapphire was steadily diluted by time, retirement, and the overwhelming gravity of the Derby aerospace empire. Yet in a strange twist of industrial fate, the engine itself outlived the nation's faith in the company that perfected it. Long after the British government decided that Armstrong Siddeley was too small to survive the economics of the supersonic age, the fundamental mechanical brilliance of the Sapphire continued to project power across the globe. The American production license had allowed the Wright Aeronautical Corporation to build the J-65, and while the British V-bombers were being retired or converted to tankers, the American twin was going to war. The J-65 became the beating heart of early American naval strike aviation, powering thousands of Douglas A-4 Skyhawks off the decks of United States Navy aircraft carriers throughout the 1960s. It is a profound historical paradox that an engine designed in Manchester, perfected in Coventry, and abandoned by the British political system ended up providing the thrust for American combat pilots flying over the jungles of Southeast Asia. Back in Britain, the Sapphire survived not in the sky, but in the quiet, temperature-controlled halls of preservation. Today, if you want to understand what Coventry achieved at the dawn of the jet age, you have to travel to places like the Royal Air Force Museum at Cosford or the Midland Air Museum, sitting just a few miles from where the engines were originally forged. Here, the Sapphires are displayed on heavy steel engine stands. Often, they are presented as cutaways, their thick outer casings sliced open to reveal the astonishing internal complexity that the Coventry machinists had to master. When you look inside one of these preserved engines, you can see the rows of high-precision axial compressor blades, still perfectly aligned, and the heavy annular combustion chamber that managed the immense heat of aviation kerosene. In the archives of the Rolls-Royce Heritage Trust, the original service manuals, engineering blueprints, and metallurgical test reports still survive, their pages sometimes stained with old oil or marked by the handwritten notes of the engineers who tried to push the thrust limits even further. This survival is not mere nostalgia. Nostalgia is a sentimental longing for a simpler past. But looking at an Armstrong Siddeley Sapphire today is a harsh, physical lesson in the brutal reality of industrial economics. The engine proves that a British factory could build exactly what the nation asked for. It proves that a group of engineers could take a terrifying new technology, the Axial-Flow Turbojet, and tame it, making it reliable enough to carry the ultimate weight of the British nuclear deterrent. It proves that Coventry possessed the raw mechanical talent to rival the greatest aerospace corporations on Earth. But the Sapphire also proves that engineering brilliance is never enough to guarantee survival. The engine could compress air, burn fuel, and produce over 10,000 pounds of thrust flawlessly, but it could not rewrite a government defense white paper, and it could not magically generate the millions of pounds required to build supersonic wind tunnels. The company did not fail because the engine broke. The company failed because the political and financial architecture of the British aviation industry shifted, leaving them on the wrong side of a state-mandated monopoly. The engine had taught Britain how to trust the axial-flow jet. It had given the Royal Air Force the power to defend the stratosphere. But it had not solved what would happen when the cost of that power became too heavy for an independent manufacturer to bear. What vanished in 1959 was not a failed machine. What vanished was the idea that a proudly independent Midlands firm could chart its own course in the highest, most expensive tier of global aviation. Somewhere in a British aviation museum, a Sapphire still rests on its display stand, the heavy aerospace alloys polished and cold under the gallery lights. The famous nameplate still bolted to the casing, holding the silent memory of a Coventry scream that the industry could no longer afford to keep. See you in the next video.